Hello there, welcome to this yet another presentation on open source design verification. This is Srini. I'm from SVA Technologies. SVA has been pioneering open source design verification flows. We are UK based, and recently we engaged with some customers through our other entity, VerifWorks, to help customers adopt open source design verification solutions, including Verilator, as well as unit testing flows and SVA linter. And my colleagues in VerifWorks, Hema, Kasturi, and Supriya, came up with this beautiful paper at DVCon India 2023. And this was presented there live, and I'm doing my bit from SVGO perspective as to how I see how this technology is evolving and how this could be a wider interest to a larger design verification community across the globe. So let's get started. So the title of the presentation is Code, Test, Verify, all for free with system builder assertions and Verilator. Though the title probably doesn't tell you the other stuff involved in open source, but fundamentally it's all about open source design verification using mainstream technologies such as assertion-based verification or unit testing flows and or top-notch linting solutions, all using open source. Let's get started. Thank you. So here's the agenda. So we're going to start with an introduction as to what the problem definition is and what's that we're trying to introduce and solve in this particular presentation context, and how did we approach as a team? How do we believe we could potentially address some of it, if not completely solve it, because this requires a wider, larger team to really solve it as we go along. And then we spend good amount of time looking at what assertion supports constructs are supported at Verilator. It's again an open source simulator, beautiful community around it. And bulk of this presentation would focus on unit testing of assertions, because I strongly believe unit tests are crucial for things like assertions, cover groups, mathlib, and things like that. So things that can be standalone tested shall be tested standalone. And excuse me. So we're going to show you SV Unit, which is one of the open source frameworks available for free. And we also engaged. I personally was spending some time porting that to Verilator. I'll share some of the success stories there, and we'll also show you how an example failed trace for a specific assertion would look like. And then we spend one or two slides on how the emerging SVA lint solutions with open source PySlint look, and then we conclude. So to begin with, why do we want to focus on design verification as a problem statement to solve using open source? Again, a lot of this great research is done by a company named Wilson Research Survey. They have been doing it for quite some time, and sponsored by Siemens, Metagraphics Siemens EDA. This work is all amazing, and it's being widely published everywhere and referred to. And it's just, I'm not going to spend all the time looking at all the graphs and over there. And again, there are excellent blogs on each of this graph that you see over there on Siemens EDA platform on their website. Please go and read it if you haven't read it. But essentially what it tries to convey the message is the ASICs and also the FPGAs, by the way. The primary reasons why they fail the first time is due to logical or functional failures. And also it shows the second graph on the top right shows you that the adoption of these various verification techniques, including code coverage, functional coverage, assertions, and constraint data. So again, today we're going to focus on assertions, which has been quite well adopted both in ASIC and FPGA. And the bottom graph also shows you that the adoption of formal with property verification is also growing very well over the years. Again, the reason why we are showing this is assertions seem to be a great area where, let's say, if you are a newcomer to the design verification domain, this could be a great area for you to pick up. You're very likely to find great jobs, high-paying jobs, and satisfactory for your career. So let's also look at the industry trends as we see it, especially globally. If you see the compound aggregated growth rate (CAGR), you see that between 2021 and 2030, we see a phenomenal increase being predicted from where we are today at 2021 at 590 billion to 1065. That's the kind of numbers we're looking at. Again, there are a lot of detailed studies over there, and you also see on the top right corner the percentage of companies that have difficulty in filling the open positions. It's an interesting one, especially again coming from academic background. If you are attending this presentation, you would see that electrical engineering, which it's a broader topic, which is kind of a broader term used in this content, this particular survey, is something very hard to find engineers on, and this is something really a good area to be studying and investing your time, and even if you are reskilling yourself, this could be a great area. And it's nothing specific to a specific country. Geographically, if you see, Japan is finding skill shortage, and that threatens the semiconductor industry from Times News. And a lot of you are familiar on following the Make in India, Make in India big move, and see how we could do this right together. So what we are trying to show here is what we can provide in assisting the industry to address the specific challenge. So let's look at the need for open source in design verification. There are multiple aspects to it, including the industry and academia view. But continuing from the previous slide on the skills shortage across the globe, specifically in the semiconductor industry, we strongly believe that the best way to address the skill shortage is to promote more and more open source, and specifically democratize the design verification learning process through various things. There's a whole lot to be done. Just one person or one team cannot do it all alone. You really need free, unlimited tools at the edge, on the cloud, and everywhere else in between. So this doesn't mean that you don't need paid tools. We do need it, but we also need to understand that there are several players here, and there are several customers who are sitting anywhere and everywhere across the globe, and these tools and the things that we are looking at for learning, to enable the learning, has to be available on the edge, which personally means, for example, in your own laptop, in your own desktop, wherever you are, as well as on the cloud and everywhere in between. Okay. So we also need to partner with content developers, promote open source mindset. That's extremely important. We can talk about more and more as we go along. And specifically, if you look at why we say that open source is better than, let's say, the cloud-based EDA being promoted by multiple other players as well. Again, clouds are great, but just be aware that there are several rural parts of the world, and you can't expect 24/7 cloud access. So again, while cloud is important, but that's not the only solution, is what we're trying to say. And with open source, you don't have any restrictive NDAs in there, so you can do whatever you want with it, specifically the MIT kind of licenses. And it encourages collaborative innovation. This is very, very important. So essentially, from an academic institution perspective, you could leverage on your various streams of students available and talent. It could be from your electrical engineering, communication stream, or computer science, or IT streams, right? The IT and CS specifically could help you fix the toolbox, for example, or additional features, addition to, for example, things like Verilate or Lint. You can also, if you're a DV engineer, aspiring DV engineer, you could put more designs to open source, and this could also be done by the industry folks who are out there and who are willing to contribute just more than their regular day-to-day job, and they want to make an impact in the industry, and this is probably the best way. And also it's most beneficial way or proven way to promote or to stamp your authority in the design verification field by saying, let's say I take up a PCIe, some IP that's available out there on the open source, and port it to something like Verilate or PySlint and things like that. Right? So with all this, you could get measurable outcomes, which again promotes everybody over there. And for again specifically for the students who are aspiring to go global, there's something called a Google Summer of Code, the GSOC, and 2023 is of course closed for the GSOC, but 2024 and beyond, GSOC takes these initiatives very seriously, and in 2023, just to give you a background, GSOC 2023 has sponsored from Google with certificate few initiatives, and one of them seems to be the SDF support with Icarus Verila. So essentially, what we are talking about is real, and if you act now and then start looking at these stuff seriously, you could be the next GSOC guy. Good luck. So what did we work on? In this context of this presentation, we're going to talk about assertions, as I mentioned, with Verilator, and also briefly the PySlint for the linting. And the unit test is what we're going to show how we tested these assertions. And it's all using open source. The FOSSI Foundation is the one that drives a lot of these. So, I mean, it's all associated with the open source design verification community, chip design industry. And as a test vehicle, we're going to use AMBA, and the system verilog assertions is what we're going to be looking at. So our approach, so we call it CIP, or our customers also call it CIP, checker IP. The checker IP is fundamentally a bunch of properties which could be classified as assertions, assumptions, as well as covers, right? That's why we call it CIP. These are fundamentally system verilog assertion based protocol checkers. And to begin with, as in any other project, you develop an assertion plan and then you code SVA. And in this specific context, in this specific project, we wanted to make sure we stick to the subset supported by Verilator. That's one thing that would strike you very hard when you start looking at open source. Not everything is honky-dory yet, especially in our field. For example, the UVM still doesn't run on open source, on the public domain at least. We do have some ports here and there, but anyway, so we do have an identified subset for Verilator. So you got to recode perhaps sometimes the assertions in a way that is Verilator friendly, which isn't that hard, honestly. I'll again show you some results. We also took up certain specific customer production proven CIPs and then ported to Verilator to prove the point that actually it's real. Right? Again, I'm going to share results. So once we did the assertion coding and it's kind of compiling and running in Verilator, what's next? How do you know that the assertions are good and they are actually doing what they are supposed to be doing? So this is where we strongly believe unit testing plays a great role. And we looked at SV unit and other available options. And it's much easier to test an assertion using something like an SV unit than trying to write a complete UVM bench for just one assertion. So we also develop pass and fail tests. Then we run and debug. We use Verilator, as I mentioned. We use VCD plus GTK Wave. If again, completely open source, that's probably your best option. There's also a tiny log-based wave tracing available. It's an interesting development by Peter Monson, and it's again a public repo available on the GitHub. Please go and take a look. It's called now it's called SV Wave Team, I guess. And we also did a brief look at available open source linting solutions for assertion specifically, and we did use PySlint to lint check SVA, and we'll show you some of the analysis that we looked at. So again, this is a sample assertion plan. The intention is not to go through all the rows over there, but conceptually what we are saying is, you look at a timing diagram like what you see on the top left corner. You start looking at each signal by signal. It's called edge by edge methodology. And then you look at each edges and then say, okay, what's that supposed to happen between, let's say, the hedge trans and hedge address, or hedge trans and hedge bus, and so on and so forth. Or what should not happen between hedge ready and, let's say the hedge trans, things like that. So you come up with a bunch of requirements, and some of these plans are again going to be available or already available on the GitHub. So you could find them. The intention is again not to go into the details of each row over here, but again, this is going to be available for you to look at it in detail. So let's take a specific assertion code that runs today on Verilator. And the intention of this particular slide is to show you that Verilator assertions we are talking something serious. We are not just talking about A == 1 or something like that. We are going to talk about a lot more interesting one. So here is an example. So there's an assertion that says AP, that's an assert and then a property, that's the prefix. AF active 1 clock, and then it says assert property, which basically says that's an assertion directive, verification directive. And disable if essentially talks about the abort condition, so not a P reset, right? And you see that there's an antecedent which basically says if I'm in the access state, so the consequent checks that from the access state you can either go to the setup state or come back to the idle state. Those are the only two options. And we also show you that if the assertion were to fail, if it is not met, we support the fail action blocks. Again, all of this is today running with Verilator. So if you can code a temporal assertion such as this and then run it on open source tools like this, there's nothing stopping you from learning system Verilog assertions for free at your doorstep. So talking briefly about the support itself, again, got to be restrictive as of today. And again, this is something that's growing as we speak. And, we do encourage the students who are, interested and capable in fixing things in the tool, please do contribute to more support. But you see that the name properties are there, signal values functions are already available, the and implication operators are supported, default clocking is supported, a bunch of them. And we do again make some notes on when we started. Some of them probably weren't working completely, and then we raised some GitHub issues. Again, it's something phenomenally working well in the open source community. You raise an issue, it gets probably fixed over a few days, weeks, definitely not months together, right? And that's very different from a traditional timeline that we are used to in the industry. And of course, there are other features that are unsupported. It's something that should be possible. Again, we encourage more contributions. So switching gears, how did we test these assertions? We use what is called a unit testing framework. It's easier than full UVM, to be honest, for testing a simple assertion such as what was shown earlier. Let's say, once you see an access state, you can either go to a setup state or an idle state, right? So you don't need a complete, driver, monitor, sequencer, agent, env, sequences, tests, and a scoreboard for it, right? You really don't need it. So what you need is a specific unit test per assertion on a feature, and it's localized test that can focus on either a pass or a fail scenario. And it's important to test both, because when an assertion is supposed to fire, it's supposed to fire. That's something you do want to test it at a unit level. And we used SV unit. SV unit is today maintained by Tudor, that you see on the right hand side as a LinkedIn post. It was developed by Neil Johnson in the beginning, and VerifWorks has already done one DVCon paper in the past in India with SV unit. So if you want to take a look at the archives. So recently, SVGo was involved in, I personally was involved in porting the SV unit to run on Verilator, and hopefully motivated the wider community to merge it or to bring all this into Verilator. And of course, he did a slightly different fix than what was envisioned. Again, that's the best thing about open source. It's not like you are individuals win. It's together we win, right? We motivate each other, we promote each other, and now the wider community across the globe have access to something that is proven, like SV unit, on Verilator. So, taking a look at a specific unit test for an AMBER peripheral bus assertion, APB. So, we're going to focus on a specific example that you see on the left hand side, a timing diagram. There's a clock, forget the address for now. Just focus on the last two signals, which is P-cell and P-enable. And basically what you're going to say is, let's look at the code. So essentially, the assertion that we are trying to test is if P-cell and not of P-enable in this current clock, the next clock have to have P-enable high. This is a mandatory requirement as per the protocol, and we want to develop unit tests, both a pass trace and a fail trace. A pass trace would look like this, what you see on the bottom left corner. P-cell and not of P-enable at a clock. After one clock, drive P-enable to 1. SVA should pass. That's kind of the expectation. Right? Now the fail trace is more interesting, and that's what I'm going to show you as a code on the right hand side. Let's look at that. The P-cell not of P-enable in the current clock, right? The next clock, we want to drive P-enable to 0, which is a violation of the protocol, and hence we do expect that the assertion should fail. So let's look at what the unit test looks like on the right side. You see an tick SV test macro, test and then end. That's the indication of a unit test, and you can see how concise this is, right? Including all the display statements. Otherwise, it's going to be even more, like 4 lines of code. That's all it is, right? So you're saying, okay, drive P-cell to 1 and then wait for a number of clocks, drive P-enable to 0 and then stay there forever. right? For 10 clocks in this case. So, and you do know that the P cell and P enable being 0 at a clock would mean that the next clock you do need the P enable to be high. And since this is a unit test intended to make an assertion failure, we drive P enable to 0 specifically, right? And hence you see that the assertion should fail, and then you would see that in the screenshots. So again, so you have a bunch of passing tests, which are called the pass tests, as well as the fail tests, the fail underscore test that you see over there. And again, a lot of these tests are uploaded on the GitHub. You can take a look, and you do see that the whole thing is nicely reported in a unit test framework such as SVA unit. It gives you various different forms, I believe HTML, probably YAML, XML, etc., etc. Right? All what you would expect. Again, all of this is for free. So, switching gears, we're looking at something new that's just getting developed as we speak. But it's good thing is it's all open source again. We're looking at linters for assertions. So traditionally, RTL linting has been extremely popular, and almost every customer uses it. Now, what about assertion linters? Yeah, there have been few available, but it's open source wise, it's a recent development, and we developed it based on Slang or PySlang. PySlang or Slang is being maintained by other great developers, again in open source, C++ and Python base. And PySlang is a layer above that, meaning it just uses the PySlang API to develop a specific system-wide test bench linter, and it's available in open source GitHub. And for this particular presentation, we're going to look at only assertion rules, but make no mistake, it has good rules for UVM, constraint random generation, functional coverage, DPIs, and etc. etc. So if you're seriously looking for anything that is, a test bench rule, it's likely that you can develop it, if not already available, on PySlang. And since it's open source, you can take a look at it. If something isn't there, you go and add it, or if something you don't like it, go and tweak it the way you want it, right? So what did we do in this particular context? We used the PySlang SVA rules to qualify the CIPs. And on the right hand side, you see the various rules that we kind of found interesting. It's not a kind of a superset of all what you did, but just some examples. For example, the naming or style checks, which are kind of good to have stuff. For example, the assertion, the asserts, the coverage prefix, etc. Right? And then you also have specific assertion, both functional as well as performance checks. You see that, for example, this should have a fail action block with, for example, a UVM error or something, right? And you don't want a pass action block because that is a performance killer. So we do have performance checks that can happen again statically, meaning it's a lint. It's not something you're going to run for, let's say, an hour and then realize your disk space is full or your simulation is running slow due to the specific assertion being added in there. So all this can happen over few minutes with open source linting, and you could find these issues and fix them before you launch your first simulation. Right? You could also find things like missing label, end label, which would help address your debug issues. So from our experience, this particular team, we requested few customizations on the naming styles because this is something we often find customers aren't happy with the built-in rules in PySlang. And the good thing is this is all customizable. Again, you just have to work with the team to make it happen or do it yourself because it's again Python and then open source. Yeah, you can't beat that. You could definitely do it yourself if you will. Right now, we are also working on building a specific VeriLater SVA subset. This could be of very good interest to the open source community because essentially, since VeriLater assertion support is still limited, for example, the sequences aren't supported, the default disable isn't supported. So you want to get an idea of what it takes to port my existing assertion to VeriLater, and something like PySlang rule deck can come and help you with that. So this is work ongoing, but this is something that we intend to do more and more work as we go along. So results wise, which is kind of where we are concluding. So we have done for various protocols. On the left hand side, you see that APB, AHB, AXI, tile link, which is the REST-V internal protocol, right? And AXI full. I'll briefly talk about what the difference is. Essentially, you see the number of assertions and the number of unit tests, and in general, for every assertion, you have two tests, a pass and a fail. Hence, if you have 12 assertions for APB, you have 24 SV unit tests. and we have completed as much as possible, and it's all there on the web. Right. Again, in case of AXI, you would see that there are two rows. There's 58 and 116, and then 156, and you see that something isn't completed. So let's talk briefly about it. AHP and APB is fully ported from a production proven CIP. In case of AXI, 58 are done. There are other, let's say another 50 of them, or 100 of them rather, sorry, another about 198 of them. They use constructs that aren't supported today in VeriLater. Hence, you will need to recode them for specific customer use cases. This is something we do it as a business at VerifWorks. If again you have a specific CIP or assertion, a bunch of assertions that need to be ported to VeriLater, feel free to call us. We'll be happy to help. So we are also working on the REST-fied tile link assertions to be ported. And the subset is identified, as I mentioned. We're working with the team, with the SVA team, to develop a rule deck around PyEsLint. So essentially, this could help you to evaluate any CIP for VeriLater compatibility, and you can also get an effort estimate of porting to open source. And we used SVA rules of PyEsLint to qualify the CIPs. So summary and next steps. So essentially, SVA and open source is today available, and it's been there for some time by now. And it's a limited subset, make no mistake, but we do encourage more contributions from whoever is attending this presentation. If you can help, that would be fantastic. The sample examples are available for free, and then the more complex ones are on customer demand. We do make it as a point that if customers want to do it, we are available to do this for them if they will. Right? Or of course, if you are motivated enough to do it yourself, feel free to do so. Right? We do want to encourage more and more collaborative innovation as we speak. So we also enable specifically the SV unit porting to VeriLater. So this is something we strongly believe in, collaborative work together. And then we used PyEsLint as an open source SVA linter, and we do encourage academia and industry to take this forward. From an industry perspective, if you are attending this presentation and you have some free cycles to do the evenings or the weekends, whenever you think you want to do it, feel free to do it, right? Please contribute. But even if your day job, if you want to run more SVA via CI/CD, which is fundamentally a continuous integration and continuous design for no additional cost, whenever you check in, you want to make sure your code adheres to a certain specific rule, let's say 10 small rules, feel free to do that using PyEsLint. That's a phenomenally good way of doing it for almost zero cost. I say zero cost because there is some cost of your missions, but the tool wise, there is no cost. And for academia, we do encourage, please add more support and also use it for teaching, because this is something we need a lot of content developers to start using these platforms available. And none of this is kind of done by one specific team. VeriLater is definitely not owned by us. It's been done by Wilson Snyder's team all across the globe. Peter Monson is one of the key guys who added assertion support, for example. Right? So we are talking about worldwide collaboration in making open source really work for the wider community to address the semiconductor skill shortage. Thank you. Please do address your questions. If you're listening to it on our social media platform, use the comment section. And if it's the live events, please feel free to ask more questions. We'll try and get as much answers as possible, as many answers as possible. Sorry. If not, we would definitely take a serious look at the questions and see how we could best address it. Thank you. Have a great day, guys.